So here's the same idea, the Bellman equations and a learning update rule, but this time with actions.
Actions.
So in the action form of it, we have this Bellman equation, the Q form of the Bellman equation. QSA equals the immediate reward plus the discounted expected value of the maximum action in the resulting state. Okay, so when we actually land in that new state S prime, we choose the action that is best for that state.
Right.
But otherwise, this is really the same kind of update as before. And so we can translate this into a TD0-like rule using the same sorts of ideas, so that we're going to have a new estimate of the value function, and the way that we're going to change it as we go from one time step to the next time step is it's the same everywhere, except for the state and action that we just left. We just took action A sub t minus 1 in state S t minus 1. And so that one we're going to update. We're going to move a little bit in the direction of the immediate reward plus the discounted value of the state that we landed in, st, where the value is taken. Is that better? It's taken with respect to the best action that we get from that state. Okay, so this is, again, the same update rule. The only difference is we got this extra little max in here to simulate the idea of choosing the best action from each state. All right, so what I'd like to argue here is that this Q-learning update rule is actually taking care of two different kinds of approximations all at one time. So let me step you through what those are, and then what we're going to do is understand how each of them works independently, and then use a result that says if these two things work independently, they're going to work together. So, all right, so here's the first idea. Notice that if we knew the model, if we knew the transitions and rewards, then when we go from some state, take an action, get a reward, go to a next state, we could actually use that to update the Q values simply by applying the Bellman equation.
Right.
All that's really happening there is we take the old Q value estimate and we update it in the way that the Bellman equation says we should update it at that particular state and action pair. And so we haven't quite argued that this works. We said that it works, but I want to dive into a little more detail on why this works. But I want to show that there's a second kind of approximation that's actually being used at the same time. So here's the second kind of approximation that's going on with the Q-learning update. It says that if we knew Q star already, we could use that to learn Q star, which now that I say it out loud seems kind of tautological.
I think it kind of is.
But I don't mean it quite so directly. What I'm saying is, let's say that we run the Q-learning update like this. We say we were in some state, we took some action, we got some reward, we ended up in some next state. We're going to update the Q value for the state action pair that we just left, moving it a little bit in the direction of the reward that we just got, plus the discounted value of the next state, st, which for the purposes of this little update rule, we're going to use the actual Q values to get that estimate. So we're kind of cheating here. We're saying we already know the Q value at least for the next state, and we're going to use that to update the Q value for the state action pair that we just left.
Right, and that would work because since we keep applying truth to it, Q star being truth, eventually you have to kind of get closer and closer and closer to it.
Yeah, and do you remember there's an important property, though, that we have to have in terms of this learning rate?
Proper subscripts?
No, you can get subscripts wrong, and you can always fix it in post.
Well, what's that property, Michael?
Yeah, so what is the property? So this is just like in the TD rule where we said that if we have the learning rate sequence sum to infinity, but the squares of that sequence be finite, then good things happen. We actually converge to the right answer.
Right.
So in this particular case, if we know what the target is, if we know where Q star is supposed to be for the next state, we can use that to actually what we're really doing here is dealing with the expectation over next states, right? And we handle that by using next states sampled from the distribution, right? Because we're actually acting in the world.
Right.
And instead of actually computing this sum, we just do this successive averaging thing, and that's going to work out.
Right. And so with insanely high probability, you will move towards the expectation.
Yeah, like probability 7.
Yeah. Yeah, that's pretty insanely high.
That's pretty insanely high.
Mm-hmm.
Yeah, so the piece that we really don't have yet to build on is this first piece. Like, what is it that's making the Bellman equation update actually converge on the solution to the Bellman equations, or Q star? And so we're going to prove that next, and then we're going to show, or actually assert that these two things can be tethered together in such a way that they're both going to end up converging in tandem.
Nice.